Okay, so I guess we're ready to state the first, define the first notion of convergence for random variables. So this is almost convergence. So again, we have a probability space. And we're going to consider some real-valued random variables. So no longer random variables taking values in abstract measurable spaces, but just real-valued random variables. x1, x2, etc., real-valued random variables. So here's the definition. So this definition is, in fact, quite simple. So the definition of almost sure convergence is as follows. You look at the sequence x1, x2, x3, omega by omega. So just look at every possible realization of the sequence. This means you have a sequence of real numbers, right? So if you had the convergence of those realized sequences for every omega, you would just have xn goes to x, right? But since in probability theory, we're also okay with having almost sure events, what we're going to have is the convergence of the realization sequence for almost every omega. That's it. So the definition is quite simple. So xn is said to be convergent almost surely if xn of omega is, so now it's a sequence of real numbers, is a convergent sequence in N, in R, for P almost every omega. In other words, the event that the limit exists, in other words, the event that the liminf equals lim sup and this is a real number, has probability 1, has probability. But how can we say that this is an event? How can we say that the event that liminf equals lim sup is a measurable set? Go back to chapter 2, measurability properties. So you have xn's measurable. Did we show that liminf is measurable in chapter 2? Liminf is measurable. Did we show that? We did, right? We did. We showed that inf is measurable, sup is measurable, liminf, lim sup, they are measurable. So if they are equal, the limit is measurable. And also we know that if you have two random variables x and y, the event that x equals y is also measurable, a measurable set. Therefore, liminf is measurable, lim sup is measurable. So the event that they are equal is a measurable set in F. So this is by chapter 2. Okay. So before saying that this has probability 1, you should tell if this is measurable, and indeed it is measurable. Okay. So in this case, there exists a random variable, let me say real valued random variable, such that the limit of xn of omega is x of omega for almost every omega. Moreover, such random variable is unique up to almost sure equality, meaning that if x prime is another such random variable, then x and x prime are equal almost surely, namely with probability 1. So we call x the almost sure limit of the sequence xn. And write that limit of xn is x almost surely. So you have an almost sure event on which you have a limit. Therefore, you can set this limit as the value of x when omega is in omega 0. And you can just set it 0 or something else. Outside this set. It really doesn't matter. As long as it is something just for definiteness, just to have a function defined on the entire set omega, just set it to 0 or 1 or whatever, some other random variable. It doesn't affect our results because this is a null set, right? This is a null set. The complement is a null set, sorry. This is an almost sure event. The complement is a null event. And since we really look at things omega by omega, we can also say that this sequence is almost surely convergent if and only if it is almost surely Cauchy. Let me say it as a remark. So xn is convergent almost surely if and only if xn is Cauchy almost surely, meaning that for every omega in a set of probability 1, you have that xn of omega is a Cauchy sequence. Because convergence and being Cauchy are just equivalent things, omega by omega. So if you have one with probability 1, you have the other with probability 1. Okay. So just for illustration, let me give you an example of a sequence that converges almost surely. Of course, just take deterministic random variables, right? Just take a convergent sequence, deterministic sequence, okay? Then let your random variables be deterministic random variables. Then you have a convergent sequence for every omega. This means you also have almost sure convergence. But let's give an example that does not converge for every omega, but almost every omega. Okay? So let's take omega as 0, 1, f as the Borel sigma algebra, 0, 1, and probability being the uniform distribution, just a Lebesgue measure. Okay? And on this, let's define xn of omega as this. So I'd like to have something that is convergent with probability 1. So rationals have probability 0, therefore irrationals have probability 1, right? So this is the part where I'd like to have convergence. And this is the part where I don't want the convergence. This is not a deterministic sequence. This is not xn is not deterministic here because I choose this if omega is irrational. I choose this if omega is rational. So it depends on omega. Although the values look deterministic, the choice of this two options is random. Right? So it is a random sequence. So if you look at omega in rationals, so you have -1 to power 1, -1 to power 3, -1 to power 5, which are all -1, and -1 to power 2, -1 to power 4, -1 to power 6, which are all +1. So this sequence doesn't converge anywhere because the lim inf is -1 and the lim sup is +1. Okay? So limit xn of omega doesn't exist. But for irrational omega, we have just 1 over n converging to 0 as n goes to infinity. So limit of xn of omega is just 0. So we have xn goes to 0 almost surely as n goes to infinity. Because rationals, the set of rationals is a countable set. You were going to ask this thing? Okay. So it's a countable set. Therefore, it is just a union of singletons. Singletons are null. Countable union of singletons is null. So what is left must have probability 1, right? Because 0, 1 is just the union of the rationals in 0, 1 and the irrationals in 0, 1. By the way, I forgot to put intersection with 0, 1. Of course, they are in 0, 1 because we work on the interval 0, 1. So this is a sequence of random variables that is convergent almost surely, but not for every omega. Okay, because there are on a set of measures 0, probability 0, we don't have convergence. Okay. So now the idea is to use some characterizations of convergence for real numbers and use those characterizations omega by omega in almost sure convergence. Okay. For instance, here's something that we can do. So recall that we have xn of omega. So if we have xn of omega converges to x of omega, so if we freeze some omega and look at this real sequence, convergence means the following. For every epsilon, we have the sum of indicators of xn of omega minus x of omega is finite. We just checked it in the first hour, right? For real sequences. Now we look at it omega by omega. We look at the random sequence omega by omega. So we can say this. So if we have convergence, then we have this. If we have this, then we have convergence for that omega. So if we have that limit xn is x almost surely, this means this is happening with probability 1. This is happening with probability 1. So now I drop the omegas because I'm writing an event. I forgot the plus infinity. So the question is, so I have uncountably many epsilons here, uncountably many. Can we take it out? Can we take it out? And can we say that xn goes to x almost surely if and only if for every epsilon, with probability 1 we have this? It's a different statement, okay? So this one is saying that with probability 1, for every epsilon we have this. what I'm proposing is to have for every epsilon with probability 1 we have this. It's a different statement. They're not necessarily equivalent, but apparently they are equivalent. This is, let's state it as a theorem. Okay, so let xn, xn is always a real sequence of real valued random variables. So let's say let x be a real valued random variable. Then we have xn has limit x almost surely if and only if. Now let me write this new version. With probability 1 we have this. So that would be a nice characterization of almost sure convergence, right? Because this is hard to satisfy. This is hard to satisfy because you would like to have a universal almost sure set that works for all epsilons. Whereas here you fix your epsilon and then look for an almost sure set. So this is easier to check in practice. You fix your epsilon, look for an almost sure set that might depend on your epsilon. Here you want to have an almost sure set that is free of your epsilon. So it is more difficult to check. So, okay, let's prove it. First of all, this side. Well, if you have xn goes to x almost surely, this means you have this. Okay. So with probability 1, for every epsilon you have this. Therefore, for a fixed epsilon, you also have this, right? So this already implies this one. So I will say follows directly by the purple thing. Okay. What we need to show is the converse. So suppose we have for every epsilon this. So if I have it for every epsilon, I can choose whatever epsilon I like. For instance, I can pick 1 over k, right? So we have the probability that this is 1 over k to infinity of xn minus x, n from 1 to infinity is finite almost surely for every k. Okay. Why did I specialize into 1 over k's? Well, now I don't have uncountably many things. I have only countably many things. K equals 1, k equals 2, k equals 3. So if I have countably many almost sure sets, their intersection is also almost sure. Countable intersection, okay? Countable intersection. So for every k, we have this. With probability 1. Okay. What are we trying to show? We are trying to show that this implies almost sure convergence, or we can show that this implies this, right? This implies this. So now we're quite close. This is for every epsilon positive. This is for every k integer, positive integer. So how can we pass from integers 1 over k's to epsilons, arbitrary epsilons? So I ruined that. take some epsilon, there is always some 1 over k below that, right? Because 1 over k converges to 0, so you can always find something smaller than epsilon. So pick k such that 1 over k is less than epsilon, or less equal, whatever. Because if you do this, so if you compare the indicator for epsilon to infinity versus the indicator of 1 over k to infinity, let me draw it like this, or slightly below, although they have the same value. Like this. Which one is above? Which one is greater? Okay. The red one is greater, right? I was indeed drawing it right. Okay. Right? Here, red one is above the black one. Here, they are equal. Here, they are equal. So indicator, let me write it in red. Indicator 1 over k to infinity versus indicator epsilon to infinity. So this one is greater. This one is greater. So if you take xn minus x, if you apply this function to xn minus x, you also have this. And if you take infinite sum over n's, you also have the same inequality. In other words, if you have this less than infinity, this must also be less than infinity, right? So with probability 1, we have that the left-hand side is less than plus infinity. So with probability 1, no, I'm arguing wrong. Okay. So since we can do it for every epsilon, what we have is that, so this property that we're trying to show is what are we trying to say? So if we have this with probability 1, I'd like to argue that we also have this with probability 1. Okay, so for almost every omega, we have that this is less than plus infinity for all k. And since for every epsilon, I can upper bound it by some 1 over k, for those almost every omegas, we also have that this is less than infinity. For all epsilon. Because I can always find some k that upper bounds it, which makes it finite. Okay? So this means we're done. We're done because this is precisely saying that with probability 1 and for every epsilon we have this. So the thing is that the fact that we are dealing with uncountably many epsilons is not a big issue because, well, all those epsilons are between 1 over k's and 1 over k plus 1s, right? So they are always between some two values of 1 over k's. Any questions? So this means we obtain the characterization of almost sure convergence. Characterization of almost sure convergence because it's if and only if. Okay. Okay. So now I'd like to discuss with you some famous result in probability theory. It is used a lot in some convergence proofs and some proofs in stochastic processes or stochastic analysis. It is quite famous, okay? So these are called Borel-Cantelli lemma. Since we're going to have two, I guess this is the plural form, okay? So first, it's going to look like it is completely off the topic, but then it's going to have some consequences for almost sure convergence, okay? So now it's going to sound like we're talking about something else, okay? So let's recall the following thing that we also used in the first hour. So if you have some random variable that is positive and finite mean, what can you say about this random variable? Positive random variable with finite mean. What can you say about that? It is finite almost surely, right? So x is finite almost surely. Okay. All we do is to apply it. Okay, application of this. Okay, so let A1, A2 be events. Take X as the sum of their indicators. So expected value of this is what? Sum of the probabilities. So the Borel-Cantelli lemma number 1, so let me write it as a theorem, although it is traditionally called a lemma. So Borel-Cantelli number 1, okay? So let, again, A1, A2 be events. So we have, if the sum of probabilities is finite, which is the mean of this x, right? Then we have x almost surely. What is x? X is sum of indicators. What is the proof? Well, the proof, there is no proof because just a restatement of the recall. With x equals sum of indicators. So there is no proof. So the nice thing about this lemma or theorem is that its condition, the sum of probabilities is finite, is just about probabilities, right? It doesn't say anything about the actual sums or anything. It's just sum of probabilities. So if you have sum of probabilities finite, then the indicators, which are indeed random variables, so the sum of their indicators is finite almost surely. So that is a surprising, seemingly surprising result. because you assume something about probabilities, and then you conclude something about the actual events. Okay? So what does that mean? Sum of indicators is finite. Let's say these are like events. A1 occurs, A2 occurs, A3 occurs. So what does this say if their sum of indicators is finite? So let's say this is a sequential experiment. So every day you want to see if AN occurs, okay? So if the sum of those indicators is finite, what can you say about this experiment? How many times do you observe this event? Only finitely many times, right? So AN occurs only finitely many times. AN. Well, of course, why do we even talk about that, right? So now, connection to almost sure convergence. It's going to have a number of nice corollaries for almost sure convergence. The reason is that you can simply take AN as the event that the difference between xn and x in your sequence, xn and x, is large. Okay? So here's the first consequence. Suppose for every epsilon, we have that the probability of xn minus x is large, so sum them over all n's is finite, then xn converges to x almost surely. Okay, so we're going to use Borel-Cantelli. This just looks like the condition in Borel-Cantelli, right? So just take AN to be this event, right? Take AN as the event that the distance is large. So then Borel-Cantelli gives sum of indicators of ANs. So what is sum of indicators of ANs? Well, it is the indicator of epsilon to infinity of xn minus x. Finite almost surely. Gives. Borel-Cantelli number 1 gives this. And this is for every epsilon. For every epsilon. Well, what is this? Sum of indicators xn minus x is finite. It is indeed what we have in the characterization theorem. Right? For every epsilon with probability 1, we have this being finite. It is indeed what Borel-Cantelli gives us. Since this was characterization of almost sure convergence, we can say xn goes to x almost surely by the characterization theorem. Xn goes to x almost surely. Okay. So these are all tests for almost sure convergence, right? You can use this corollary to check that some sequence xn converges to some random variable x. it's a sufficient condition for almost sure convergence, right? So if you know the distributions of xn and x and calculate xn minus x greater than epsilon, so this is going to give you some function of n, right? And then you take infinite sum over all n. If it turns out to be finite, you can say that xn converges to x almost surely. So that's a calculus type of test, right? So you calculate some probability, you calculate an infinite sum, and if it turns out to be finite, then this means you have almost sure convergence. So instead of going through like an epsilon definition of almost sure convergence or something like that, you just have a more useful way or practical way to check almost sure convergence. Okay? And there are two more such corollaries of Borel-Cantelli about, again, almost sure convergence. Okay. So here's one corollary. So suppose there is a sequence epsilon n of strictly positive numbers such that the limit of epsilon n is 0 and I forgot the indicators, epsilon n to infinity of xn minus x is finite, then xn converges to x almost surely. Oh, I wrote something wrong, right? I should have written something with probabilities, sorry. Of course, if we look at the indicators, then this is not really a test for convergence. Okay, so this just looks like the same type of test, but now with changing epsilon. So now we're going to take just this event in Borel-Cantelli, now with epsilon depending on n. So Borel-Cantelli 1 with this condition gives that the sum of their indicators is finite, almost surely. So this means almost surely the difference between xn and x is less than epsilon n for all but finitely many n. Or let me say, after some, let me write it like this, for large n, for large n. Namely, there is some index after which you always have this property, right? Well, since epsilon n goes to 0, by assumption, so since we have this, we must have xn minus x goes to 0. Again, everything is almost surely. And this just means xn goes to x. Again, almost surely. So there is a similar version of this corollary, which I will just state without proof. So suppose there is a sequence epsilon n of strictly positive numbers such that the sum is finite and the probability that xn plus 1 minus xn is large, so the sum of those probabilities is finite, then Xn is convergent almost surely. And I will leave it as an exercise, but you should use the test for convergence in real numbers. So we stated some test for convergence, which really looks like this. Sum of epsilon n's is finite, and we have a property to check for convergence of real numbers. Now, this is a combination of that test for convergence with Borel-Cantelli. So indeed, this Borel-Cantelli is going to give you, so the application of Borel-Cantelli to this is going to give you exactly the sufficient condition appearing in that test for convergence. Okay. And so that is it about the consequences of Borel-Cantelli number 1 for almost sure convergence. And we are done with almost sure convergence. But there is a second part of Borel-Cantelli, which is interesting for its own sake. So I cannot just skip that number 2, because it's also a famous partial converse. So if you look at Borel-Cantelli number 1, this says that if sum of the probabilities is finite, then sum of indicators is finite almost surely. What if this is plus infinity? What if this sum explodes? Okay? So partial converse to Borel-Cantelli 1. Okay? And this is Borel-Cantelli number 2. But now we have partial converse because we need to have independent events, be independent events, meaning that their indicators are independent random variables. Independent events. So now we have this. So we have, if sum of probabilities is infinite, then sum of indicators is infinite, almost surely. So it is really the opposite of what was written in Borel-Cantelli number 1. This was finite almost surely. Now it is infinite almost surely. So two extremes. There is nothing like it is finite with some probability and infinite with some other probability. It is really 0-1 type of law. The sum of indicators, if you have independent events, sum of indicators is either plus infinity almost surely or finite almost surely. Okay? So it is very extreme. So let's show that this is finite with probability 0, okay? Let's show probability that this is finite is 0. What is this? Well, we said that this means it happens only finitely many times. Namely, after some index, it never happens. It never happens. So there is some index after which it never happens. Okay? Convince yourself that these two things are equivalent. So the sum of indicators is finite means what? There is some index after which you never have that event happening. So it is always the complement that is happening. Okay? So let's just call it Bn, okay? So we have B1 smaller than B2, smaller than B3. They form an increasing sequence of events. So this is indeed the limit of the probabilities of those intersections. What we're going to claim is that the probability of this intersection is always 0. For every n. So limit of zeros is 0. Okay? Every term is going to be 0. Okay? So let's calculate this. Since these are independent events, I can write it as product of probabilities. Although you might say I'm cheating because I'm using the infinite version of this product rule. So I leave it to you to verify it in the infinite case. Of course, this needs to be checked. This is an infinite version, but maybe using some monotone convergence arguments, you can prove it. Anyway, so this is n to infinity, 1 minus probability of ak, right? And now comes the beauty of this proof. It has a very original and nice idea to use the relationship that 1 minus x is less than e2 minus x for positive x. Well, you might say, who came up with that, right? Why e2 minus x? Well, of course, this is an idea that some people figured out. And if you use if you use other functions, maybe you don't get the result that you want. So you need to think carefully to bound it in the right way. Sorry. So this is less than e to negative probability of ak. Why did I choose exponential? Because I'd like to pass to summations. Product of exponentials is exponential of summation. And since this infinite sum is infinity, after some index, it always has to be infinity. So e to negative plus infinity is 0. And we're done. This, if you'd like to have a picture for these functions, so let me, e to negative x is, something like this, right? Or no, like this, e to negative x. Let me draw it like this, okay? E to negative x. So when x is 0, this is 1, and then x goes to infinity, this goes to 0, okay? And how about 1 minus x? Well, at 0, it is 0, right? Sorry, it's 1. At 0, it is 1. And then it decreases like sorry, like this, right? Good. So it's going to cross this axis at 1. Yeah, 1 minus x is less than e to negative x. Is it wrong direction?
In the when you were showing the
Okay. Okay. Did I use it the wrong way? No. 1 minus x is less than e to negative x, right?
So that should be less than. We have written equal.
Okay. This should be less equal. Okay. Thank you very much. Thank you. Okay. Good point. Okay. Right. We're done. Next week, we're going to discuss convergence in probability convergence in LP, and convergence in distribution. 3 more.